Hey guys, so we're going to continue our talk about acid and base chemistry by delving into buffer solutions and titrations and how those two topics kind of go together. So at this point, you should be pretty familiar with buffer solutions. We've talked about them for a couple classes. You've actually made some in the lab, you've played with them. So I really want you to recall that buffer solutions consist of conjugate acid-base pairs in solution, and they can resist pH changes by reacting either the conjugate acid or the conjugate base with whatever solutions you're adding into them. So if you're adding an acid to the buffer, then the conjugate base is going to react with that acid to hold the pH pretty steady. And if you're adding a base to the solution, then the conjugate acid will react with the base, again, to keep the pH pretty steady. So buffer solutions are buffering pH changes, they're resisting pH changes by reacting either the acid or the base that's present in their solution with whatever you're adding to it. Now, let's consider the titration of a weak acid with a strong base. So you're going to have the weak acid inside your beaker or your Erlenmeyer flask, and your strong base is going to be inside your burette. Initially, your pH is going to be less than 7 because you have a weak acid in your container, and that's the only thing you're measuring. You've added no base to it whatsoever, it's just the acid present. And we all know, whether it's a strong acid or a weak acid, the pH of acids is less than 7. Now, as you start to add the strong base to your solution, it will be a slow addition because you're doing a titration and you guys are being very careful about this. And your pH is going to increase really gradually as the strong base is being added. Now, that's because as you add the strong base to the acid solution, you're going to start to react the acid with the base. You're going to end up making the conjugate base of the weak acid, and that gives you a buffer solution. Because if you remember, the definition of a buffer solution is that you have a conjugate acid-base pair in solution to resist pH changes. So as you add more strong base, you're going to have resistance to a pH increase. You're going to have a really long flat region on your titration curve. Now, eventually, you're going to add so much strong base that you're going to overcome your buffer capacity. There will be too much strong base there. The weak acid present in solution will no longer be able to react with it, and then you're going to have the pH rise pretty steeply afterwards in your titration. Then you're going to go up towards your equivalence point and then past your equivalence point, just like any other titration you might do. Now, talking about it, you probably can't really see what's happening inside the beaker or on a curve in your mind. If you guys have done the lab, maybe you have some sort of idea of what I'm talking about, but not everyone will have done the lab yet. So let's go on. I'll show you a demo curve, just an example here. So again, we've got our pH starting off as less than 7, so we've got some sort of acid here. And because there's a buffering region, I know that it was a weak acid, and you're adding a strong base to it. Now, if the situation was reversed, if you had your strong base, if you had a strong base present inside your beaker or your Erlenmeyer flask, and you had a weak acid inside your burette, do you think you would end up creating a buffer at any point during the titration? You wouldn't, because you would already have so many available hydroxide ions, those OH ions from your strong base, that they would react instantly with any acid being added, and you wouldn't end up making that conjugate acid-base pair in solution. It wouldn't happen. Getting back to the titration that we have here, the curve that we've got in front of us, again, starting off with some sort of weak acid, you're adding a strong base to it, you're increasing the pH as you go up and towards the end. Interesting things to notice are, as I mentioned previously, the creation of a buffer, labeled here as a buffering region on the graph. And you'll notice that at one point in that buffering region, your pH is going to be equal to your pKa. This is referred to as the half equivalence point, and it exists when the number of moles, or the concentration of your weak acid, is equal to the number of moles, or the concentration of your weak conjugate base that you've created here in the solution. The other point that's interesting to label and good to note on your graph is the equivalence point, and that's when you have equal amounts of acid and base in the solution. That's when your reaction has actually happened and completed. Now, in this case, because you're titrating a weak acid with a strong base, the pH of your equivalence point is going to be greater than 7. So all of you have done the lab where you titrated sodium hydroxide in hydrochloric acid, strong acid, strong base, and you know the pH at the equivalence point was 7 because it was a strong titration. When it's a strong, weak titration, that equivalence point pH is going to shift up and down, so you really have to think about what kind of indicator solution you're going to use in these titrations. Phenylphthalein isn't always the one that you're going to use. There's actually a huge range of different indicator solutions that you have to think about, you have to peruse through, you have to decide what's the most appropriate, what's going to change colors, where you think your equivalence point is going to happen. And that choice of different indicators and that range of different pHs of equivalence points is why we make you guys do all these different calculations before you start doing any lab work. It's why we put you through the paces and make you crunch out numbers every time. It seems pointless. There's actually a reason. If you didn't have the appropriate indicator in your beaker when you're doing the titration, you would not know the right time to stop. You wouldn't know when you actually have the same number of moles of acid and base when your reaction has completed. Now, I mentioned previously in the class that there's kind of like a little cheaty equation that you can use when you're doing acid-base titrations and you have a buffer solution. And I think some of you actually heard me name it as the Henderson-Hasselbalch equation. Now, as I said, this is only to be used when you have a buffer solution happening inside your beaker. It is not applicable any other time. The only time I want to see you writing things out with the Henderson-Hasselbalch equation is when you know you have a buffer occurring. Now, how do we get to that equation? Why is it useful? Well, you can write out the dissociation of some sort of weak acid with water here. You've seen it previously. You know that HA reacts with water to form hydronium and A-, that's your conjugate weak base. There's an acid dissociation constant that goes along with that reaction. It lets you know how strong the acid is, how willing it is to dissociate in water to form that conjugate base and hydronium. Now, we can take this expression, this Ka, the acid dissociation constant, and rearrange it in a way that makes it kind of more applicable and more useful for us when we're talking about buffer solutions or conjugate acid-base pairs. So you can see on the next line how I've pulled out the concentration of hydronium from the expression and moved the Ka, the acid dissociation constant. So we've isolated a term that has HA and A-, the concentration of our weak acid and the conjugate base pair. So you can take the log of this expression, and because the log of the hydronium concentration is the pH, it's a really handy way to find the pH when you're going through with a buffer solution. So as long as you know your concentration of your weak acid and its conjugate base, you can look up whatever your Ka or pKa is, and you can determine the pH from there. Now, just a fun mathematical quirk, like I mentioned previously, at the half equivalence point, when you have the same amount of A- and HA, so that's your conjugate base, and your weak acid, your pH is equal to pKa. And that's just a mathematical thing, because if you take the log of 1 here, that turns out to be 0. So then pH is just equal to pKa. Now let's go through and talk about how you can actually use this expression and when you should use the expression. So like I said previously, only use it when you actually know you have some sort of buffer solution going on. In this example, we're asked to calculate the pH during a titration of 40 milliliters of 0.1 molar of HPR, so prussic acid, a weak acid, with 0.1 molar NaOH, which we know is a strong base, when 30 milliliters of base has been added. So we've already added some amount of our strong base to our weak acid. We know that means that there's going to be conjugate acid-base pairs in solution, and it might be that there's a buffer situation happening. So here, you'll see something that looks very similar. We've worked with ice tables previously quite a bit, but when you're determining if you have a buffer solution or not, it's almost easier to work with an ICF instead of ice, so ICF, initial change and final, instead of ice. Because you're not at equilibrium, things are reacting, they're not going to go backwards. Here I've simplified it just to before addition, the addition, and after the addition. Note however you want. Just it's easier if you're working in moles in this kind of table instead of in concentration. So it's not a true ice table, you're not at equilibrium, you're not working with concentrations. We can go through and calculate the number of moles that we had of prussic acid HPR initially. So it's just taking the volume, multiplying it by the concentration. So we know how many moles we have, and we can put that in for our before addition. That's our original scenario. We wouldn't have had any hydroxide. We wouldn't have had any PR negative, none of our conjugate base. And water is a pure liquid, so we don't really care about it in this kind of table either, just like an ice table. Now, in the addition, we're adding sodium hydroxide. The sodium, not really that important in this case. We just mostly care about what's happening with hydroxide ions. And you can figure out how much we're adding by taking the volume again, so it's 30 mils, multiplying it by the concentration, 0.1 moles per liter, and we find out how many moles we're adding into the solution. Now you'll notice that this arrow just goes one way, not back and forth. It's not a reversible reaction. We're not going to react PR negative with H2O to create hydroxide and prussic acid. That's unfavorable in our solution. One more reason we're not working with an ice table, like I said before, it's not going to be at equilibrium. It's a one-way reaction. So our weak acid is going to react with the base, so 0.004. It's going to react with 0.003 of our base, leaving us 0.001 of the acid. All of the base is going to be consumed because there's more acid than base in solution, and as it's consumed, it gets turned into the conjugate base. So we end up with 0.003 of PR negative. Now, if we look at how our concentration of acid and concentration of base compare to each other, they're in the same volume, so it doesn't really matter if we divide by 70 milliliters in the end. That would be the 40 we started with plus the 30 of base that were added, because it is in the same flask. We can just work with the moles here to get our ratio between. So now we know the amount of weak acid and conjugate base that are present within our flask. We can compare these amounts to figure out if we have a buffer or not. So if we can use our shortcut with the Henderson-Hasselbalch equation, or if we can't, we've got to create an ice table and go through all of that. So because these two species are present in the same solution, they have the same volume. We don't have to take these moles and divide it by the volume to give us concentrations for this calculation. The volume would actually cancel out. If you want to, you can take these two different mole values and divide by 70 milliliters, but it's not necessary. If you want to do the shortcut like I did here, just divide the amount of acid by the amount of base, and you'll see that works out to 0.33. Now, if you remember, a buffer tends to resist within the 0.1 to 10 range. That's equivalent to a pH change of plus or minus 10. So because we're within that numerical range, it means we have a buffer solution present within our flask. Since there's a buffer, it means we get to use the Henderson-Hasselbalch equation, which I've written out here on this line. So it's the concentration of hydronium equal to the Ka, the acid dissociation constant, plus the ratio of our weak acid over its conjugate base. Now we can just fill in the different values down here. So 0.33 is what I found above. It's the ratio of the weak acid to conjugate base. And then 1.3 times 10 to the negative 5 is the acid dissociation constant of prussic acid. You can look that up in your textbook if it's not provided in any questions. Go through, do the math, and you can see that the pH ends up being 5.37. That's actually a 5 there. Sorry for my poor writing. Now, why do we care about the pH when we're not at the end point, when we're just creating a buffer here? Well, it's nice to know what pH values to expect as you go through titration, so you can identify if anything's going really off the rails, if there's some huge problem happening in front of you. Also, you might titrate just to get to the end point and figure out concentrations, or you might set up some sort of titration just to get a buffer solution. So it's nice to know what pH ranges you're going to have in case you need to select an indicator to identify when you're in a buffer range. That's about everything we're going to talk about here with buffer solutions and titrations. There are some activities posted for you to work through and prepare for the next class. Have a good night.